Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year, we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen.
Well, good morning or good afternoon, depending on where you are based. So welcome to this webinar on innovative mini-grid projects to accelerate renewable deployment in islands and remote communities. So before we start, just repeat some of the things that you saw on the video. So we are recording this session, and we'll send you the recording. So you'll be able to see that in the next few days, and the slides. And please don't forget that today is your chance to actually send questions to our 3 experts, who I'll ask now to introduce themselves very briefly before we start with the first presentation. And we also have a tradition here at ATA Insights, which is that we ask the members of the audience to to say where they're joining from. Today I'm joining from Berlin in Germany. So, okay, I'll stop sharing my screen now so you can see all the panelists, and well, welcome the 3 of you. So let's start with Peter. Peter, could you tell us briefly who you are, please?
Sure. Thank you, Carlos, and a very good afternoon to everybody in the webinar. My name is Peter Goh. I am based in Singapore, and I'm a vice president with the Sunseep Group. We are a leading solar solutions provider serving the Asian region. Thank you.
Thank you very much, Peter. And Wilhelm, can you please introduce yourself briefly so the audience know who you are? You're on mute, by the way.
Peter, you want to go first?
If you want, no.
Beni.
Yeah. Well, Beni's presentation is first, but I just thought if you want to, just a couple of words. But yeah, Beni, if you could introduce yourself briefly, please.
All right. Thank you, Carlos, and hello, everyone. My name is Beni Suryadi. I'm Indonesian and based in Jakarta, Indonesia. I'm a research manager for the Power, Fossil Fuel, Alternative Energy, and Energy Storage Department at the ASEAN Center for Energy. We are an intergovernmental organization in Southeast Asia region on the energy cooperation. Thank you, Carlos.
Thank you very much, Beni. And Wilhelm, I don't know if you'd like to introduce yourself briefly before we start with the first presentation, which will be Beni's.
Sure, thanks, Carlos. My name is Wilhelm. I'm located in Singapore. I'm with Wärtsilä for the past 4 years. My background is in engineering, product management, and design of battery-based and renewable energy systems. And today I'm responsible for Southeast Asia and Northeast Asia for any kind of application of grid-tied and islanded ESS applications.
Thank you very much, Wilhelm. So, Beni, whenever you're ready, if you'd like to start sharing your screen, and we'll start with your presentation.
All right. Thank you again, Carlos. Thank you very much to ATA for having me in this important event. together with William from the Wärtsilä and Peter from the Sunseep. I assume everyone can see my screen already, and for the next 10 minutes or so, I would like to share some information about the ASEAN practical experience and prospect for a renewable deployment in the isolated island and rural and remote area in this region. As you know, that Southeast Asia region, or also popularly known as the ASEAN, we have 10 countries, and it has a huge range of the geographical situation. And many of the with the many archipelago, and then many of the population are living in the rural and remote area or the isolated island. Is this slide? I have introduced myself. I'm working for the ASEAN Center for Energy. In case you are not familiar with our name, institution name, that it's kind of the IEA, but we are in the regional context, the Southeast Asia context. We are working closely with the Ministry of Energy and all the relevant government institutions on energy issues from all of the 10 countries. Our direct boss is actually all of the 10 ministers on energy from all of the 10 countries in this region. We based in Jakarta, and then we act as a think tank, a knowledge hub, and catalyst for in implementing the so-called regional blueprint on energy cooperation for all of the countries in this region. Here I'm sharing with you the study that we are presented, launched last year at the 37th ASEAN Minister on Energy meeting. This ASEAN Energy Outlook, perhaps to some context is similar with the many outlook that you have seen, you are familiar with. But what makes it it's different that this is the outlook is being developed officially with the policymaker, with the expert from all of the 10 countries. So it's being developed intensively with them, in the consultation with them. So it's really reflecting the current situation in the three countries and the future trajectory up to 2040s. So in this outlook, we also were working on the 4 modeling scenario reflecting the plan and ambition of the countries at the national level and regional level at the various topics, in particularly on pushing more renewable energy penetration and stepping up the effort in reducing the energy intensity. You see the number on 2025 and 2024. In all scenarios, fossil fuel remains as the major type of energy in the region, be it from oil, coal, or natural gas. But we can also see that how renewable energy can be pushed to higher here, considering the potential that we have in this region, the existing policy or the planning incoming policies the government is developing, the available incentive, as well as the technology development among other issues. This week, I think most of us hear about the new launch of report by IEA on the net zero in 2050. We are in the supporting on this game, but we also believe that there are many issues that need to be addressed first, especially in this region. And one of it is about electricity access, providing the electricity to the people in this region. As everyone knows, the electricity is fundamental to the socio-economic development as an important inputs to modern lifestyle, livelihood, education, and health for many issues. And as the government work to grow the economy and meet the myriad of social and environmental objectives, the provision of electricity is among the fundamental services that enable the progress. We have seen in 2018 that around 95.5% of region population have access to electricity. I mean, we may have some debate or discussion on this calculation number or how you define the electrified or not. But we have seen the good progress that we have. But we also still have a huge number of people living without the access to electricity due to, in large part of the extension of the service to rural area, remote area, and isolated island, which become the main discussion from our topic today. But the national grid expansion have driven the larger trend, while the falling cost of renewable energy, energy-based mini grid, and the standalone system, combined with the growing regional technical capabilities, capacities, have made the off-grid solution increasingly become viable option for a difficult area that I mentioned earlier. So as you see that the population of people without electricity access is concentrated in the 5 countries. Of course, we are not talking about the Singapore, but the other countries in the region. But many of them is living in the rural and remote area, in the isolated area that needs to be fulfill their needs on the electricity access. So that's why last year we also conduct a study and also released a study that on the practical experience and prospect for the electricity accessibility, electricity access in rural and remote area, as well as in the isolated island in the ASEAN countries. So in this slide, we're talking about the arrangement in the rural and remote area. That you can see that the identified solution that we have listed from many cases that we have collected in ASEAN countries. So we have collected a number of the case studies, various rural and remote area, and then make case analysis to identify the base case applications. And then while each rural and remote area have their own specific case, but we can see the pattern, and there's studies that to identify a number of solutions that we can have, like the prioritize the source construction of load center on synergetic development of both grid and power source to provide electricity in remote area, or the grid extension, or the off-grid system, as well as micro grid. And one example in this rural and remote case is electrification in the Rain, Cambodia. This is lying in the southeastern part of Cambodia and bordering with the Vietnam. It's about 3,000 kilometers square with a population about 352,000 people. So the national grids cover only the cities and the towns. So we're talking about the distance. So most of the village has no electricity access. Why we can identify that the technological solution is being provided is a combination of the national grid extension and construction of the mini grid. This is what the option that was adopted. The plan was for the national grid to increase around 250 kilometers of MV lines, the installation of 390 kilometers of LV lines and voltage regulator, and expansion of the capacity is around 6.42 MVA distribution for farmers. It's like a budget from around 9.7 million USD and financed by the ADB, and it provides a socio-economic benefit, provide the 24 hours electricity to around 88,000 households locally and meet the basic demand for the electricity. So this is a good example where the international financing supported the extension of local grid and the construction of the mini grid for the village. And another one is on the isolated island. So we also compile many cases in this region on the isolated island, and then, but we can also see the distribution case from few examples that we have. And one few example that we have is we are talking about the Karimun Island in the is about 80 kilometers from North Java Island. It's the total area is 70,000 kilometers square and has around population is also quite small, actually less than 10,000 people. But this is the tourism potential area, so the demand on the electricity is also high. On the onset of the electricity development, the local government installs 3 small diesel power plants. Then the electricity was delivered to the household through a medium voltage grid. However, since the capacity, the source was very limited, so the electricity was provided only around 12 hours a day. But this is the case until 2016, because in 2016, the utility took over the electricity program. They installed 2 diesel power plants, and then to also in 2019 they installed solar 3 megawatt peak solar PV and 4.5 megawatt hours battery as the alternative source to the diesel power plant. But we have seen that the proper states is being adopted to promote the electricity access progress on the isolated island, starting with providing the basic needs, bringing adequate and reliable electricity together with a lower tariff that considered in the second stage, and then at the optimal production cost to be addressed in the third stage. And here will be my last slide. Talking about the providing electricity through renewable in this rural remote area and island. We have seen and identified many challenges and opportunities. Detail of it can be also read from the report that we are releasing. We have identified 6 points. But one item from the list that I would like to highlight as the most connected issue with our discussion today is the disconnected between a grid development and off-grid power solution provider must be addressed. The off-grid project often focus primarily on supplying electricity in the short term, and not attention is paid to many other things, also legal, technical, financial parameter for the future grid integration and post-connection operation. We also identified the government need to the risk of grid investment with the transparent grid extension and off-grid planning, a regulatory framework for eventual grid connection, or talking about the financial mechanism, so that private investment is not hindered due to elevated risk factors. This ends my presentation. I'm happy to join the discussion later. I'm pass back to you, Carlos. Thank you very much.
Thank you very much, Beni, for your presentation. Very interesting, and well, as I said before, I encourage everyone in the audience to send in the questions, which you can do through the Q&A box at the bottom of your screen. And next up, we have Peter Go. Peter, please, whenever you have you're ready, start sharing your screen. I can see it.
Okay, well, participants of the webinar, a very good morning, Singapore time to all of you. I'm Peter Go from the Sunseep Group, and thank you to the organizers for inviting me to share about Sunseep's experience with Singapore's first utility-scale energy storage or ESS testbed. Before I dive into the ESS topic, please allow me some time to share about my company. All right, sorry, some transition issues. Sunseep is a proud Singapore homegrown company. We are a full-spectrum clean energy solutions provider with regional presence in 11 countries. With more than 2 gigawatt peak of solar capacity contracted as of 2020, we are Singapore's most established solar PV developer. And we serve a wide range of clients, ranging from homeowners to small and medium enterprises, to government-linked corporations, to government agencies, multinationals, the likes of UTC, Amazon, Apple. And we are supported by an extensive network of shareholders, financial institutions, and business partners. These include our shareholders such as Temasek Holdings, Banpu, Sumitomo, Datco, and etc. So since our inception in 2011, we have always been known to be a solar company. However, over the course of the company's growth, we have expanded to offer the full end-to-end range of clean energy solutions. These include energy retail and clean energy retail. So we provide clean energy to the likes of Apple, Google, Facebook, Amazon, to businesses and to homeowners. Energy efficiency solutions through energy performance contracting, whereby we finance and retrofit M&E equipment such as lighting and ACMV systems and co-share resultant cost savings with our clients. Green roof solutions, EV charging solutions. We also do in-house R&D on the digitalization of energy by applying machine learning and artificial intelligence. And last but not least, energy storage systems and microgrids. We feel that ESS is an important element of the big sustainability picture. We believe that sustainability is multifaceted. It's not just about clean energy generation, but also about demand-side management and energy storage. We look at how we can integrate ESS with PV systems to form microgrids to improve energy resilience and reduce reliance on the grid. ESS also helps to manage the intermittency issue of PV systems. We started our ESS journey back in 2019 with the Pongo Distributed ESS project. As the contractor, we deployed a 100 kilowatt-hour system across 5 residential blocks at the Pongo Waterway Estate. With the utility ESS project, Sunseep was the principal investigator and deployed the 2.4 megawatt-hour ESS system connected to a 66 kV substation. In the next quarter of this year, we're looking to deploy a 1 megawatt ESS system with 300 kilowatt peak of solar PV to form a microgrid to provide power to the jetty area of Pulau Ubin. So for our international audience, Pulau Ubin is an offshore island from Singapore. And in Q4 of 2021, we will be deploying a near-shore floating 1 megawatt peak of solar together with ESS at the southern tip of Singapore. So we move on to Singapore's first utility-scale ESS project, which we are very proud to be involved with. This project is jointly funded by the Energy Market Authority of Singapore and SP, Singapore Power. It is a 2.4 megawatt-hour lithium-ion battery storage system connected at the 22 kV grid level. As the principal investigator, we are responsible for the installation and operation of ESS. Our co-investigator, the Nanyang Technological University, oversees the development of an ESS model to predict battery health and performance. This project is still ongoing and moving into the operational phase. I have listed down a few expected outcomes and learning points for today's sharing. Firstly, the development of a UESS model for state of charge and temperature prediction for fault diagnosis and risk assessment, so that we can understand and we can see what is the typical ESS performance in Singapore's hot and humid environment. Secondly, we want to optimize operational efficiency and offers into the electricity market of Singapore. This allows us and future operators to assess commercial feasibility of ESS and future deployments. Do note that the optimization portion was also covered in the Pongo DESS project, but it was purely a simulation. And lastly, we wish to identify and resolve regulatory requirements over lapse or redundancies due to the nature of ESS as both a load and a generation source. There are multiple regulatory hurdles that we had to clear and deconflicting that was required. I'm sure Wasila will be very aware of this because we worked together on this project. And we had to go through SCDF, SP, EMA, PSO, and EMC. We also had to clear BCA and NEA during our construction phase. Again, for the international audience, we have many abbreviations in Singapore. So it is thus important for these knots to be untied before mass deployment in the very near future. The system has only just commissioned, so I'll share some of our experience up to today, starting from the design stage. The very first challenge we faced was finding land or the space for the ESS. Singapore is a very dense urban setting, unlike an offshore island, so very dense, lack of space. And our original site location was an open air sheltered space, as you can see in the photo on the right. However, this site was rejected because it was not completely exposed to the sky. So not only must there be unrestricted access to fire engines, it must also be fully exposed. Thankfully, another site was made available to us, so that's where we are now. And we understand that this decision was due to fire safety concerns, especially since this ESS was the first of its kind in Singapore. But there are not that many substations in Singapore that are completely exposed. And this ties in with optimizing the efficiency of the ESS. What do I mean by that? So utility ESS are most effective when connected to a node when there is a need for grid support services that an ESS can provide. For example, a substation serving a district that is being redeveloped or for industrial use. The substation may not have a piece of empty land for the ESS to be installed. So this is something that the grid operator and regulators have to consider for future mass deployment. Especially so in Singapore, we have a target of 200 megawatt by 2030. Next is regarding the fire rating of the battery container compartments. Our latest fire code introduced a max cap of 600 kilowatt hours per compartment, which based on our understanding references the US standards NFPA 855. But we do know that the NFPA allows exceeding the capacity if the system undergoes additional tests and risk analysis. For such safety concerns, not only can we refer to the US standards and local fire code, and more recently, Singapore has a TR77 standards for guidance. Next is the HVAC or cooling and ventilation requirements for the battery container. So for cooling requirements, I think quite self-explanatory. Lithium-ion batteries need to be kept cool for safety issues, also to maintain efficiency and prolong lifespan, especially so in this part of the world where the climate is very hot and humid. Next, on to ventilation. Our current fire code requires battery rooms to have ventilation. The keyword here is rooms, which means that people can walk into the battery container. It is like a room and treated like a room where people can work and enter inside. So we had this initial design, but we then changed it to a non-walk-in design where the doors are located along the entire length of the container and the racks can be accessed from the outside. We feel that this is much safer, and I think it will be also more preferred by the authorities as compared to the walk-in version. Next, on to technical standards. We had issues getting the power conversion system approved as there were no local standards, even though the PCS is a mature product with international standards. The reason behind this is quite technical, which has got to do with earthing and insulation. But the gist of it is that local standards in Singapore do not cover the PCS. And as a result, our local QPs or qualified persons that are not familiar with the equipment are hesitant to endorse it. Again, with the development of Singapore's new TR77 standards, this will help to align the industry on which equipment is acceptable in the local context, and that will help to smoothen future deployment. Moving on to the design, from the design to the installation and testing stage, the main issue we had during installation and testing was the lack of local contractors and qualified persons who had experience or confidence to take up the work. A lot of hand-holding was required from us, and especially by the equipment suppliers. At this juncture, a big shout out to our EPC partner, Wärtsilä, for this project. They have guided us along as well. We also faced a lot of logistical issues due to COVID. For example, we could not bring in any overseas experts, so we had to do a lot of calls through video calls, and the guidance was done overseas across different time zones. But thankfully, we were able to witness the FAT, the factory acceptance test for the critical equipment before the pandemic. There are solutions to these issues. Firstly, local expertise and capabilities need to be developed, perhaps by making training courses available. Secondly, factory testing should be available locally, especially after the pandemic period, such as developing FAT facilities in Singapore. And this will be the same for some of the other countries that was mentioned by Beni. I think that local expertise and capabilities will be very important to ensure smooth deployment of ESS and microgrids. So in general, I think we are moving in the right direction. Moving on to operations, we are just in the midst of commencing operations. So let me share what some of the things that we're currently going through. Firstly, in Singapore, there is a long list of registrations and licenses that we have to apply. And this list is basically same as what is required for a power plant, because the ESS is recognized as a generation facility. We feel that the process might be necessary for a power plant, but if the intention is for ESS to be more widespread, then these administrative processes must be streamlined. Such process is also complicated by the fact that ESS is both a generation and a load at the same time. Some expected operational costs for the system are transmission and grid charges, as well as monitoring, maintenance, and market participation costs. In terms of revenue in Singapore, the ESS can currently only provide regulation and maybe reserve, which based on last year's estimates per megawatt hour is about 12 to 20 Singapore dollars, which really isn't a lot if you think about it. So this is something that the industry and the regulators need to figure out. What are the services which will be in demand, and to establish market mechanisms for ESS to be commercially viable. For example, ESS can also help to defer upgrades and grid infrastructure. So perhaps there should be a fixed fee to be paid to the operator through its lifespan. So with all that being said, the Singapore government clearly spelling out its near-term and mid-term green plans with solar and ESS, amidst many others, here at Sunseep, we definitely wish to help facilitate widespread deployment of and commercialization of ESS. This includes regulatory frameworks for the ESS having to be clearly defined, a separate category to represent ESS as both a load and a generator, to address the ESS limitation by differentiating them from conventional generation companies. The energy market also needs to recognize and reward the ESS for fast sub-second response. A separate grid support service category that remunerates ESS based on response time, as there's the lack of land space, distributed ESS, nanogrids, and even floating ESS should be considered in Singapore's context. And lastly, government subsidies for facilities to encourage behind-the-meter ESS for peak shaving. I've come to the end of my presentation. Thank you very much once again for allowing me to share Sunseep's experience. And we're happy to join the Q&A later, and I wish everyone a pleasant day ahead. Thank you.
Thank you very much, Peter. Very interesting, and I'm curious to hear about some of the ways to overcome those regulatory challenges or suggestions you may have for how things could be improved on that front. But before that, we'll have Wilhelm's presentation. So Wilhelm, and remember you're on mute, and yeah, I can see your presentation, but if you turn it to full screen. And well, in the meantime, I can see it now. It's on full screen. So whenever you're ready to start, please go ahead.
I hope you can hear me and see me.
I can hear you perfectly.
Thanks again for two excellent presentations so far, giving me a great ramp to just continue what has been presented before. I would like to quickly introduce Wärtsilä for those who don't know. It's a company with about 18,000 employees around the world, and has in about 180 years ago plus started to manufacture engines mainly for the marine business, but then quickly also moved over to the land to use them in power plants. And nowadays, as a logical consequence, Wärtsilä has started about 4 years ago to introduce batteries as a combination with engines. And very quickly, we have found out that that expertise, the ESS business, is very well applicable to engines, but also other applications which can be standalone for grid support or even mini grids, what we're talking about here. So what I would like to go through with you, just talking a little bit about the importance of the software side of those mini grids, because we believe that this is widely underestimated. Software is keeping everything together. It runs everything. It looks for efficiency and covers also local standard requirements. Then very quickly again, I would like to show you a picture of that Singapore system, which Peter has greatly introduced. Then I would like to go a little bit deeper into an application in Africa, which is a mine in Fekola. And lastly, I would like to share with you a little bit of data about our mini grid system in Graciosa, which is in the middle of the Azores, which is in the middle of the Atlantic Ocean. But quickly to give you an overview about ESS applications, we're very happy that we just cracked the 1.5 gigawatt mark in terms of systems being either in operation, deployed, or contracted. You can see on the left, the majority by now is happening in the US. This is a very vibrant market for various kinds of ESS, including a lot of mini grids, mainly in the Caribbean. But also Europe and Africa become very active. Historically already, UK started years ago with a storage market, but also Germany was following very quickly. But even though you don't see many dots here in the Southeast Asian region, it has been growing very, very quickly. You see that our pipeline alone is around 1.2 gigawatts. About 350 megawatts have been either deployed or are already in operation. The reason why there's not so many dots is most of them are under NDA. We keep that very serious, and we'll talk about that once things have been released. But just for you to give you a little glimpse, at the bottom right, you see a picture of a very interesting system, which is in the Philippines on a barge. It's a floating ESS, which is sitting next to a larger power barge containing two huge engines supplying about 50 megawatts of energy to the villages and towns located very nearby. So as I said before, talking about software, GEMS, the Greensmith energy management system. Greensmith has been the company we acquired about 4 years ago to actually get all that expertise and knowledge into our company. And that software is about 10 years old, in its 6th generation now. And what it really means is what you can see in the picture here, that orange circle, is that all the components you would have in your mini grid system is not only energy storage we talk about. You have to manage the input of wind, solar, thermal generation as in engines, but not only make it possible that they are compatible with each other, you have to make good choices which component to use when, to keep longest lifetimes, to keep efficiency high, to keep also fossil fuel usage low, and to lower operational times of those high maintenance parts of it. So these softwares do contain power plant controllers, of course, which then includes virtual power plants. So these softwares are replicating the actual system in a virtual way, making decisions what to do next, and then giving commands out to all these components to make them work together. So that another part here is a fleet controller. If you have multiple of these systems, you can actually observe what happens to them on one screen. And a grid controller makes it possible that we take care for the energy storage system, the solar system, everything together on the individual grid connection point to not only fulfill requirements, but also not have any negative impact on the grid they're connected to, and which is a huge microgrid in this case. So if we look into a couple of different applications, specifically on the right-hand side, you see all those islanded applications, what we're talking about today. So it is not only island grids we are talking about here. We're also talking about applications such as a black start, if a larger grid actually went down. They also have to have the capability to stepwise or in one go start up a grid again. So islanded grids are actually very complex, but that's exactly what we're looking for, because this software can handle complex solutions in a very, very efficient way. And you will see that a little later, specifically on the Graciosa example. So this one here, I don't need to say much about it. I just would like to underline again, some of you might ask themselves, why are we talking here about a grid connected system while we're talking about mini grids? Well, I think Peter has summarized it pretty well. All the challenges they went through in these systems do equally apply to mini grid systems. And just as an example here on that picture, you see on the left-hand side, the battery container. In the middle, you see the power conversion system, which is the inverter and the switchgear. On the very right-hand side, you see the transformer separated by those walls, and that's where it all starts. Each location where you're deploying mini grids have their own requirements, their own standards, and here those walls were necessary for local fire protection applications. So every country is very, very different and specific in what they require. So a lot of adjustment to those needs is necessary here. The Fekola mine in Mali in Africa, I think that's a very nice example about using multiple assets in one mini-grid application. This is pretty large here. You see it's a 13.3 megawatt, 15.4 megawatt hour energy storage system. It is connected to 30 megawatts of solar and 64 megawatts of engine power. Again, the interesting part here is actually the software, which handles all those components at the same time, makes very intelligent decisions about not only what we do right now, but also what happens next. So a lot of forecasting is included here as well, both on the demand side, but also on the weather side. So here is the system I would like to look a little bit deeper into. As I said, Graciosa is an island in the Azores in the middle of the Atlantic Ocean. It, just in a nutshell, eliminates the use of 17,000 liters of diesel per month, which is quite a lot. You see further down in the gray box a little bit of a summary. The power plant consists of 4.5 megawatts of solar and 1 megawatt of wind and 6 megawatt or 3.2 megawatt hours of energy storage. And the background here was that at the beginning, there was only the engine power plant, and the intention of the operator here was simply reduce levelized costs of electricity, but also the pure dependency on fuel. So the decision was made that 65% of the consumption should be covered by renewable energies. You see here then what has been deployed under usage of the existing engine power plant. And just to give you another picture of that, that's what it looks like today. The wind, the energy storage system, engine power plant, and PV plant are working all side by side, controlled by the GEMS power plant controller. So it optimizes not only the dispatch, but it also does load forecasting, which we will see in a second. It will do renewable weather forecasting, and it also provides all the interfaces and a collection of all data for analysis, which then enables also remote operation and maintenance. So on the left-hand side, you see a very interesting curve. I quickly explain that. So in yellow, you see the solar curve. You see in blue, the wind curve. In green, the battery contribution. And in brown, the diesel. And the interesting thing is here that you can see that for a long period of time, the whole island is purely running on renewable energies. And we have just received the message, the system is running a little bit more than a year now, so about 1.5 years, but we have now achieved 140 days of pure renewable energy operation. So this is a great outcome. So again, we are not only talking about here becoming green in our mini grids, we are actually looking at the possibility of running 100% renewables for a very long time. And this has been something which has been discussed for decades. It was always a big wish to make that possible. I know that I have here also in the audience an old veteran, Manuel Celia. Hi, Manuel. We've been working on power plant, on power systems on islands 15 years ago and have made that possible in a small version. But then it even wasn't possible to run on 100% renewables, but nowadays it is. So that is a great achievement. On the right-hand side, you see what's most important in those systems, keeping first of all the frequency very stable, which is an indication of is there enough energy or is there too much energy? And then we need to accordingly react on that. And also keeping the voltage stable, which is in both cases, frequency and voltage, not an easy task in mini grids. If you switch one big load, those two values do fluctuate quite a lot. So that's the main control issue, but the software controls that very well. Forecasting, I said that before. First of all, load forecasting is very important, that we know that we have enough assets running when a bigger load is actually started. So the system is a learning system. It learns from the past and projects that into the future. And we see the same also for renewable energy forecasting, just simply being connected or learning from own weather data we have measured, or if you are connected to a weather data service, then you can equally use that very well. The last slide shows you a little bit of a comparison of the outcome of this system and its installation. And we have made a little bit of a comparison here to stay a little bit more objective in terms of costs. So the blue bars are an assumption for 0.74 US dollars per liter of diesel. The orange ones are 0.96 US dollars per liter of diesel. And if you run only engines, you see that the costs have been very high. We have made projections. If you add storage to the engines, it is a little bit lower, but wouldn't completely justify the investment yet. But if you look into engines plus storage plus renewables, then this really lowers the costs by more than 30%. And the outcome here has been tremendous. So I hope in that short time I have been able to give you in a nutshell a little bit of an insight here. Of course, always open for questions, and thanks for listening.
Thank you very much, Wilhelm, for your presentation. Very interesting. So, right, so let's jump right into the questions from the audience. So, one of the questions I have received through the various platforms is how these projects that combine mini grids, renewables, battery storage, how do they support economic development and sustainable economic development in Southeast Asia? Don't know who would like to take that question first.
Carlos, maybe I just starting the discussion to respond. Just recall back from the example that I'm sharing on the case that we have in rural area in Cambodia, countries that they five rank. It's quite difficult for me to pronounce. But as I said earlier, there are around 352,000 people living in this area. It's quite a distance from the cities, so they don't have no access to electricity at all, and then it's quite hindering the potential for them to grow on the economy, on the social development. But with this model that being implemented, the solution is being provided, the combination of the national grid extension and the construction of the mini grids, then the cost is around, say, 9.7 million USD. But then it turns to be able to provide a 24 hours electricity to around 88,000 households. To meet the local, the energy, not only for turn on your lamp or for the basic needs, but also to spark the economic activities. So this is providing a level where it can push the economy to grow. The user of the this extended grid pay around 17,000 kilowatt hours. May see whether it's it's higher or low.
Beni, you have pressed the mute button by mistake, I think, or somehow.
Oh, great.
There we go. I can hear you now. That's okay.
Yeah, sorry about that. I don't know whether others that, but the community is paying around 17 cents per kilowatt hours. We may have a different point of view whether it's high or is it low. What this is within the range for them is on their willingness to pay based on the various economic analysis that we have. While it's compared, we can say it's very cheap compared to the previously, where the user is using only the mini grids powered by diesel generator, and they pay $1 per kilowatt hour. So you see how much the gap, the economic benefit that's generated from this, and in turn it's become a push for the economic development in this area. So this is why how we can see this kind of the projects, like Peter mentioned a number of projects in Singapore, or William mentioned in other area that really benefiting the society as all. Thank you, Carlos.
Thank you very much, Beni. I don't know if anyone else would like to answer the question. Otherwise, we can go to the next question. Which, well, I think there is a related question there, which is how, are these what makes these projects viable, and how they are an alternative to a grid connected, to being connected to the centralized grid. Well, there's certainly a good alternative economically, if you compare it to diesel generators, because 17 cents per kilowatt hour compared to $1 per kilowatt hour is significant. But yeah, Wilhelm, I know you want to say something.
Yeah, of course. I think it's a really good question. It depends on a couple of factors. So I would just like to start with what I ended with in my presentation. So if you compare fuel-powered supply, which we will find in Southeast Asia a lot, even in public grids, then renewable energy supply either connected to that grid or separately in mini grids can make a lot of sense. But it is also very important to identify how far away are you from that grid, and how much does it cost you to actually connect with a transmission line. And a few years back, I've been in a group trying to investigate, is there a number you can tell? And you can say that globally, it starts to make sense purely from the transmission line point of view. Let's assume the electricity cost would be the same, that if you're further away than 2.5 kilometers from a public grid connection, then it certainly makes sense to have a look into renewable energies. So in other words, if we look into our region again, and we're talking here in Southeast Asia about 20,000 islands, South Pacific has another 20,000. It's incredible potential. So all those islands nowadays are no-brainers, right? So a lot of them are actually running already on renewable energies completely because it is cheaper. So, and that is also should give us a little bit of an opportunity to clean up a little bit of a rumor that solar and batteries would be still too expensive. I just would like to give an example on the battery side of things. When I started here with Wärtsilä, the average battery price was lying somewhere around $550 per kilowatt hour, which is now anywhere between 150 and 200. So it is a tremendous price drop, and it is always worth it to, from year to year, reinvestigate again what those components do cost. So there are a couple of variables, but everything points into the direction of considering seriously mini grids and or renewables.
And Peter, I don't know if you'd like to add to this question, or
perhaps not at this juncture. I think Beni and Wilhelm have covered
okay,
all the grounds. Yeah.
Great. So Wilhelm, you mentioned something really interesting in your presentation, which is that before, when you did mini grids, it was not really possible to go 100% renewable, but now it is. So what has changed?
Well, it's again, it's never one single little answer to that. Certainly pricing, that has changed a lot. So in the past, when I started after university, I worked mainly with wind turbines, and all the engineers developing them and also the operators were always saying it is a big dream if there would ever be a big battery to smoothen the output of a wind turbine. Today it's possible, right? Because technology has advanced and pricing has advanced. And we all know that this is, of course, with the support from other industries as well. But that's where we are today. And that's why it's actually viable. There are business cases behind that. And it is also that on the other hand, there's a completely different thinking. In the past, there was only fossil fuel, and the thinking about other things didn't really make sense because they weren't properly explained. Nowadays, we are thinking much more sophisticated and positive about these solutions. So we are always looking into that direction.
Okay, thank you. And Peter, I have a question for you. So you mentioned that you had multiple regulatory challenges when you were developing your project in Singapore. So could you just give us an outline about what those challenges were, and any sort of like, well, if you have the ear of a regulator, any kind of general recommendations for making it easier to install this type of project, whilst of course still respecting all of the safety requirements and everything that is required.
So one of the biggest challenge came from the fire. Well, in Singapore we call it the Civil Defence Force, which looks into fire hazards, because there's common understanding that ESS is a flammable product. So down to where it's supposed can be installed, where it can't be installed, the various fire suppression systems that have to be used, that itself took months, if not maybe almost a year. And I think that is the biggest hurdle for us in a dense island setting. I think if you're in a remote island, it may be a little bit more relaxed in terms of the regulation, because there's just not that many people where the plant is. But in this case, the ESS is next to inhabitants, and these are high-rise buildings. So that once the fire starts, it can catch on quite easily. So there's a lot of concern on that. But I guess with technology improvements of the ESS systems, and also the way the system is being designed, and good fire suppression systems, good quality products, that risk can be kept to a minimum. Thankfully for us, because the project was government funded, the owner is actually the Energy Market Authority of Singapore on completion of the project. So they themselves, being a government agency, they were able to help us to communicate our issues and our concerns to the other government agencies and help to bridge that communication gap.
Okay. Thank you very much, Peter. I was looking at the questions we have here, and I think there is an interesting question here about the ownership of systems. And it's a question by someone called Rosa, and Rosa is asking, in each of these core scenarios, who was the final owner of the assets, and do you see any potential conflicts of interest between the owner when the owner differs from the operator?
So perhaps let me share that for the system that I have mentioned, the 2.4 megawatt hour system, the owner is the Energy Market Authority of Singapore and Singapore Power. We are the operator in this case. But moving forward, our business model, commercial model for ESS, our preference is to build, own, and operate, a BOO model, as opposed to just being an EPC or just an operator. Now, if you talk about conflicts of interest, I think there will be some fundamental conflicts, because the owner wants to maximize profits, right? The operator gets paid to operate. So there are fundamental differences, and we don't want to get into that. So our preference, like I said, is to do a BOO model.
Thank you, Peter. And there is a question here which I find very interesting as well, which is on the land use and how expensive it could be in a place where there is not much space. So the question is by Kingsley, and it says land is usually expensive on islands. The savings you showed, do savings show the cost of land buying or leasing? Well, I mean, to that I would also answer that you showed a floating storage system, which I found interesting, but I'll let you answer.
Yeah, so first of all, I think it's a very good question, and it reminded me also directly of the barge we've provided there, and that was exactly the reason. There was simply no land. Other reasons are sometimes, which is can be a little funny, but it's actually that islands sometimes don't have the possibility to unload these heavy loads directly on the shore. So they have to sit on the water because of coral reefs, because of other reasons. I think we should also consider that any kind of energy supply will need space. So what I'm saying here is that whether you are deploying wind turbines, storage, solar of course uses a little bit more, that's true. but any kind of energy supply will need its space. So we shouldn't forget that. So the difference is not 0 and 100%. The difference is somewhere in between. It will certainly cover a part of that as well, a part of those costs, but we all agree that those costs of land can be very, very different from location to location. So it's very hard to answer that, but it's certainly covered in parts. If I may, Carlos, there are 2 questions I would quickly like to answer.
Yes, please.
In the Q&A.
I think, we can, if everyone agrees, we can spend another 10 minutes or so answering questions.
Sure. So one is, could ESS be increased to more than 100 megawatts? The answer is we are working on ESS systems with a size of up to 700 megawatts right now. So the reason why that is possible is simply that energy storage systems are modular. So you would use blocks of 2 or 3 megawatts with associated power conversion systems and batteries, and you just use them as often as you want. The question is rather, does the substation you're connecting to, is that possible to take all the energy and the power? And if that is possible, and the subsequent injection into the grid is possible, then there's no limitation. The other question was, could fuel cells be considered for those applications in a similar way? Well, practically yes. They can be used in terms of energy storage, but also releasing in a controlled way. But from the technical perspective, you have to make sure that they have the same response times and flexibility like energy storage, right? I mean, storing hydrogen in fuel cells is a little bit tricky, or besides fuel cells, so to speak. And releasing the energy through the fuel cells also takes a little bit of time. So I think the applications are slightly different. So at the moment, and that might change, at the moment, lithium-ion batteries are probably the best way to go in terms of response times in combination with their costs.
Thank you very much, Wilhelm. I think, there are various questions that have to do with business models and how sustainable it is, what streams of income you could get from these projects. So I know, if you have a battery that is connected to a central grid, it can provide different services. So in the case of these systems, which are in a mini grid, and one of the main considerations when you think of the improving the business case of these projects. Don't know who'd like to take that question.
Peter, if you would like.
Perhaps let me share more on the commercial viability of the grid tie system first. So I have to mention that firstly, the ESS that we have done with Wärtsilä is charged by the grid, and we're using it to provide ancillary services to the grid, and that's where our source of revenue comes from, frequency regulation and so on and so forth. At this very juncture, to be very honest, it is not entirely commercially viable by itself, because when you charge from the grid, it depends on local regulations for country to country, but in Singapore, we have contracted capacity charges on top of transmission charges, on top of energy charge. So the cost is quite high, but when we discharge the grid, whatever we're getting paid for, the revenue is quite low. And this is not even talking about CapEx on the battery system itself. And if you look at the lifespan of the battery system, if I were to say 10 years, actually, it will be loss-making. So how can we improve this? We need to find more revenue streams for the ESS system, not just in terms of frequency regulation, but other forms. For example, are we able to do peak shifting and so on and so forth? Now, for an off-grid system, I think it is a lot more straightforward, because I may be wrong, please correct me. I think the only income stream is when you sell energy to the users directly. And this is the model that we're trying to do in the offshore island in Singapore. So it's really about the cost, the CapEx, and the OpEx versus what is the cost per kilowatt hour they are selling it to, you're selling it for. So that will be my take, and I'm happy to hear from Beni and Wilhelm.
I pretty much agree with your explanations there.
Great. So, well, I mean, there is another question here which I hear quite a lot actually. So maybe Wilhelm, I think you'd be in a position to answer this. So, T. Bakalu asks that, well, he says diesel generators provide good stability of system in terms of inertia. How would renewables manage system stabilization without much inertia? So
it's a great question. First of all, battery systems as such cannot provide inertia like engines or wind turbines do, because they have the rotating mass, and that rotating mass could spin with a little bit of power provided to them for a quite long time. The inertia as such, and the reason why it's necessary in a grid is you want to prohibit the frequency dropping down from its nominal value to 0 within milliseconds. You want to create a natural ramp with the mass still rotating slower and slower of your engines and turbine. So you can replicate that behavior with storage systems, but of course storage is limited, so that application is limited, right? So once you have used the energy there, then this isn't available in the next half hour, for example. So that's why we clearly have to distinguish between inertia, natural inertia, and synthetic inertia. So it can be provided to a certain extent, but not to the extent of engines and wind turbines.
great. Thank you. Thank you very much. And well, I mean, unless you want to take another question, I'd like to close the webinar with a general question on what's driving the uptake of these systems in Southeast Asia. So I think you have mentioned in many cases cost, and it supports economic development. One of the main things that the main drivers behind the uptake of these systems, which it is happening, because you mentioned, I think I saw on your slides, Wilhelm, like 1.2 gigawatts of projects in Southeast Asia. So it is significant.
Yeah, I think that is something Peter can also answer very well, because they are located in all these countries. But the only thing I would like to say here is that it has a lot of historic reasons, because most of the countries we're looking into here, specifically Thailand, Philippines, Vietnam, are countries with dramatically increasing business and income, and that means the energy consumption in those countries was rising very, very quickly. And that means that those grids, which have mainly not properly been maintained, suddenly need a pretty quick extension and renewal, so that the introduction of those means is a no-brainer. And this is where that number of deployments in the region is mainly coming from.
Great, thank you very much. I don't know if whether Peter or Beni would like to add to this. Beni, you were on mute, by the way. I don't know if you wanted to.
No, I have no additional point to being addressed well by Wilhelm.
Thank you very much, Beni. Well, I think, Peter, do you want to say anything?
I fully agree with what Wilhelm has mentioned, and I think the next 3 to 5 years will be a very exciting time for ESS and microgrids in the Asian part of the world. I think there'll be exponential growth, and that will be something that will be good for not only the companies, but also the people and the economy. So we're looking forward to being part of that journey.
Thank you very much, Peter, for your answer. And well, I'd like to thank everyone who's been with us today in this webinar. I think it's been very interesting. I'd like to remind you that you will get an email with the recording and the slides as well. And well, and thank you to you, Beni, Peter, and Wilhelm for for sharing your knowledge with us today.
Thank you, Carlos. It's been a pleasure.
Thank you, Carlos, Wilhelm, and Peter as well. Thanks,
Thanks, guys.
Thank you very much. I hope to see you soon.
Yes.
Bye-bye.
Thank you. Bye-bye, everyone.
Bye-bye. Have a good day.